Hello, students. You have now completed, I believe, more than 1.5 weeks of this course, and I hope you are now able to appreciate how light interacts with matter, how stimulated emission differs from spontaneous emission, the important role that a cavity and population inversion play in the context of laser, or how the integration of a cavity and a population inverted medium is the key to the working of a laser. So we can now move to the second part of this course, which is to know the working of a variety of important lasers that are in operation today. However, before we do that, I would like you to have a fairly good idea the behavior of light. Perhaps you have had some course on various aspects of light when in your uh, high school physics, or perhaps you must have taken some course on light even in your undergraduate classes. But I would like to enlighten you in the next few lectures some important properties that light exhibits. Let us begin from reflection of light. You see, when light shines on a surface, part of it, a fraction of it, small or big, actually returns back to the incident medium. This is called reflection of light. But whenever we talk of reflection of light, we must consider three different kinds of surfaces: a smooth or polished surface, such as that of a plane mirror; an opaque and rough surface that is abundantly present in nature and normally characterized by micro irregularities that is not visible to the naked eye, and which is of course abundant in nature. For example, even the page of your paper, on which probably you are taking note of this lecture. And the third surface is an interface which separates two optically transparent medium, that is medium 1 and medium 2, which could be air and water or air and glass. So reflection from such interface, reflection from a very plain and smooth surface, and reflection from an irregular surface. Such surfaces are plenty, abundant. Let us consider first a smooth surface. When a parallel beam of light shines on such a smooth surface, then the incident ray and the reflected ray make equal angle with the normal on the reflective surface. Such a reflection, where angle of incidence and angle of reflection are same, is called specular reflection. A bright and sharp image is often formed from such a reflection, and an example is shown here for an object, the expanse of which is not confined on the smiling toddler alone sitting on this reflector. This is the reflector mirror, but stretches as far as the spotless blue sky, which of course is not seen here, but the reflection of the blue sky is clearly evident on this mirror. In contrast, when a parallel beam of light shines on an irregular surface, as is the case with most natural objects, different incident rays, as you can see, will meet the surface at different angles, and thus will be reflected in all possible directions. Although all these reflections follow the rules of specular law of reflection, that is, angle of incidence equal to reflection. But because the reflected rays travel in all directions, this kind of reflection is often termed as diffuse or non-specular reflection. This diffuse nature of reflection makes it possible for us to perceive the endless beauty of the nature. As a case in point is this exquisite Mandarin dark shown alongside. Daylight shines onto this magnificent creation and is reflected from every conceivable points of its body part, revealing in turn its dazzling color for eyes to our eyes from any position, because the reflected ray travels in all possible directions. This thus reveals in turn the uniqueness of nature, such reflection. When light travels from one medium to another, in contrast, when light travels from one medium to another, let us now consider the third case, that is the reflection that is occurring from interface of two media. For example, you have one medium here, and this is medium one. Light falls on you. The part will be reflected. If this is a smooth surface, then it will follow the specular law of reflection. Angle of incidence will be angle of diffraction. However, a part of light will bend and move to the second medium. This is called diffraction of light, which we will learn in a while. So this occurs from the interface between two media. The formation of image and most of the time the interface actually is air and water. The formation of image on air-water interface is a very common sight in nature, and it owes its origin to the reflection of this kind. For example, you see, this adjacent picture captures a sharp image of the Great Pyramid of Giza as a result of the reflection of light from absolutely calm and wriggle-free air-water interface of River Nile. So what happens? Suppose this is our pyramid. And this is the water surface. So the light ray from the pyramid, sunlit pyramid, actually will be reflected from the water surface and reach our eye. And we will see the image under the water. So this will be the image that is formed as a result of reflection on the air-water interface. Now you can clearly see that the intensity of this image is much less intense compared to the actual intensity, brightness of this sunlit pyramid. That is simply because when the sunlight falls on the air-water interface, only a part of the light is actually reflected into the air to reach our eye. Rest of the light actually escapes into the water. And that is why the image is not as bright as the sunlit object. In contrast, you can see in almost the entire light is reflected from the surface of a mirror or polished metal. The image can therefore be just as bright as the object, as you can clearly see in this picture, which is formed as a reflection of light on a polished surface like mirror. There is yet another kind of reflection that is known as retroreflection. You see, the surface of some surface, the structure of some surfaces may be such that reflected light travels exactly in a direction opposite to that of the incident light. The reflection exhibited by such a surface is called retroreflection. A retroreflector is often a combination of two mirrors inclined to each other at right angle. Reflected light here, it is easy to show, straightforward to show by using the rule of reflection laws, and some standard geometrical rules, that reflected light here always travels in a direction exactly opposite to the direction of the incident light. Here the incident light comes in this direction and the reflected light goes back exactly in opposite. This property, as you can see, has been underlined here for two rays of light. One is this, the other is this, striking the mirror at different angle of incidence. They're different. Well, let us very quickly prove this, that in a retroreflector, the reflected light always travels in a direction opposite to the incident light. In retroreflector, as I say, the two mirrors placed in such a way that they are perpendicular to each other. Now you see, this is our retroreflector. And suppose a ray of light falls on this mirror. So after the reflection, it strikes the second mirror at this point. It will be again reflected. Basically, we'll have to prove that this and this are parallel. The incident ray and the reflected ray are parallel. Then only reflected ray will travel in a direction opposite to the incident ray. Now this is 90 degrees. And this is the normal to the reflecting surface. So angle of incidence, let us call x, will be equal to angle of reflection. Now because this is perpendicular to this and this is also perpendicular, so these two rays are parallel. Therefore, this angle is also x. And if this angle is x, if we draw a perpendicular, then this angle too is x. Because this and this are equal. Therefore, if we extend this way, this angle and this angle are also x. So then this angle is 2x. Which is same as this angle. So that means this ray and this ray are parallel, because this is 2x and this is 2x. From the law of similar angle property, we can say that this ray and this ray. Therefore, when two mirrors are inclined at a right angle to each other, then it works like a retroreflector. I should mention here that later in this course, you would see that how the positioning of a retroreflector on the surface of the moon made lunar image ranging by laser possible to an incredible accuracy. Let me just mention here that David Scott, an American astronaut who commanded the Apollo 15 lunar mission, had placed such a retroreflector on the surface of the moon precisely on July 31, 1971. The unique property of such a reflector to return the reflected beam in the same direction as the incident beam allowed later the measurement of distance between the Earth and Moon to an incredible accuracy of just 2 centimeters, which is equivalent to an error less than even 1 part in 20 billion. I will just very briefly explain to you how this retroreflector helps the estimation of distance between Moon and the Earth. So, on Moon, a retroreflector was placed. So, retroreflector is essentially two mirrors which are inclined at right angle to each other. Now, from the Earth, a helium neon laser beam was aimed from an observatory of Earth to this mirror, which was placed there by that Mr. David Scott. So this will then will be reflected. The reflected ray will travel exactly in opposite direction and reach Earth. So from the travel time, if this distance is d, then the light actually traveled the time from journey to and fro journey, if it were t, then in this time the light traveled twice the distance between Earth and Sun. And therefore, light's velocity is c into 2t equal to, c into t equal to 2d. In this time, light has traveled 2d distance. So d would be simply equal to ct by 2. So this retroreflector allowed this measurement, because else light would have escaped anywhere and it would not have reached back the surface of the Earth. And of course, you needed a highly directional beam of light so that when it reached back on the Earth, there is enough light so that it could be detected. Now, another point that I would like to mention here, that David Scott today is only one of 4 surviving moonwalkers today. Now, refraction of light. When light is incident on an interface between two media, a part of the light is reflected back in the medium that we have seen, and the remaining light exhibits bending before traveling into the second medium. The phenomena of this bending of light as it travels from one medium to the other, the interface, is called refraction of light. Snell, a Dutch physicist, first established the relation between angle of bending with refractive indices of the two media, which is now popular as Snell's law of reflection. According to this law, light bends away from the normal when traveling from denser to rarer medium and vice versa. Let us just make use of Lenz's law and prove this. Suppose we have two media, refractive index of one media is mu1, the other is mu2. And let us assume mu2 is greater than mu1. That means this is denser and this is rarer. Now light travels, light is incident from the denser medium. This is the normal. And first let us assume it is just mu2 mu1. Let us not bother about which is denser, which is rarer. So after this diffraction, let us assume light bends away from the normal. Let us assume that angle of incidence is I, and angle of refraction is R. So it has bent away from the normal after the refraction. Now Snell's law says that mu2 sin I is equal to mu1 sin R. So now that means it says that refractive index into sine of incidence angle must be equal to refractive index of the second medium and product of refractive index of the second medium and the sine of angle of refraction. Now let us assume that the light is traveling from denser to rarer medium. That is, mu2 is greater than mu1. If mu2 is greater than mu1, then to keep the product same, sin I must be less than sin R if mu2 is greater than mu1. Now, value of sine of an angle increases with the increasing value of the angle. Therefore, if sin I has to be less than sin R, I has to be less than R. So we can say that when light travels from a denser medium to a rarer medium, it bends away from the normal because R is more than I is less than R, and vice versa. If it would have been the other way, if mu2 would have been less than mu1, that means this was rarer, this was denser, then light would be bending towards the north. So when light travels from denser to rarer medium, it bends away from the normal, and when it travels from rarer to denser medium, it bends towards the normal. This we can infer from Snell's law. Now, from here, we move into another kind of reflection. So, we now study yet another kind of reflection, which is called total internal reflection. As we know from Snell's law, we just learned that the light rays bends away from the normal when it travels from a denser to rarer medium. Three situations have been depicted here in that case, where the light is traveling from denser to rarer. For most of the incident angles, it follows the laws of reflection the right way. That means it bends away from the normal and it follows the Snell's law. However, if we continue to increase the angle of incidence, then we will eventually reach an angle of incidence which is called critical angle, theta c. Then the angle of refraction becomes 90 degrees. It is possible. You are increasing angle of incidence, so angle of refraction also will increase. Eventually, for a particular angle of incidence, the refracted ray grazes over the interface. So the angle of refraction now is become 90 degrees. What happens now? If you just increase the angle of incidence above theta c, above this critical angle, then there is no more scope of refraction of light, because angle of refraction has already become 90 degree. It cannot now become less than 90 degree again get back into this medium. So if we increase the angle of incidence beyond critical angle, the entire light then will have to return back to the incident medium, as there is no scope of further refraction of light. So this phenomena rightly is termed as total internal reflection. Means the entire light is internally reflected back into the incident surface. There is no refraction of light. Total internal reflection is the key to transmitting light through an optical fiber strand that is transparent to its wavelength. How do you do that? Well, I will very qualitatively explain. So how does light travels through optical fiber? By exploiting the property of total internal reflection. Let me just very qualitatively explain. This is suppose the optical fiber, which is usually made of glass, and we launch our light at an angle of incidence which is more than the critical angle. So light will be totally internally reflected. There cannot be any refraction of light because the angle of incidence is more than critical. So this is air and this is glass. Glass refractive index is more than that of air. So light is traveling from denser to rarer medium. That is what should be. That is what should happen in case of total internal reflection. So the light is totally internally reflected. There is no loss of light through refraction. And it again strikes the other interface between the glass and it will again be, this angle of incidence will again be the same, that is more than the critical angle. It will be again reflected. And it will actually travel through the fiber through such zigzag path and eventually will reach the other end without any spillage of light through refraction. And if the wavelength of light is chosen in such a way that this material of the fiber, that particular glass, doesn't absorb any light at this wavelength, then the light will propagate down the fiber without any spillage due to refraction and without any loss of energy due to absorption, because we have chosen a wavelength which is not absorbed by the material of the glass. So then light actually travels from one end of the fiber to the other. And this length of the fiber can be enormous, hundreds of kilometers. So you can actually send your information to this light. And because light's frequency is much higher compared to microwave or radio wave, you can actually dump much more information, data, this light. Well, this optical fiber communication forms the backbone of today's communication network with the capability of transmitting seemingly endless data at the speed of light, crisscrossing the globe in the blink of an eye. You would learn more about this when we study fiber lasers later in this course. The other important property exhibited by light is called dispersion. This is a rainbow, the multicolored, exquisite arc of light thrown on the sky when sun shines on the raindrops has over the centuries fired the imagination of thinkers, the scientists, and the poets alike. The origin of rainbow was finally cracked in 1672 when Newton proposed the theory of dispersion of light. He showed that the sunlight is white and is made up of 7 colors, which are violet, indigo, blue, green, yellow, orange, and red. How did he prove that? He actually allowed sunlight basically travel through a prism and found that the white light is split into all these constituent colors. But we can actually explain this. This is called dispersion of light. We can actually explain this dispersion of light simply by invoking Snell's law of refraction. Let us try to quickly and qualitatively understand the underlying physics of this dispersion of light. You see, you suppose take a surface which I've shown here as air and glass, and you shine it with your white light, which is incident at an angle say I. And air and glass is denser than air. So the ray will, if it were just a single color ray, it will just bend towards the normal. This is the normal. Now, if this light has so many colors, will all the colors bend equally? What I mean is that would the angle of refraction be same for all the colors? No, they are not. It is known that light, red light, travels faster, a little faster in the glass, and violet light is the slowest, and all other colors speed lies in between. But what does it imply? So the obvious question that we need to ask here is whether all these colors, that is violet, indigo, blue, green, orange, red, will they have, will the glass offer same refractive index for all of them? The answer is no. You see, refractive index is basically defined as the ratio of the speed of light in aqua divided by speed of light in that. Refractive index of a medium is defined. Now it is known that the red light travels a little faster and violet light is the slowest, and all other light speed lies in between. So that means what? If red light speed is the highest, then mu of red, if this is the highest, then the ratio will be the smallest. So mu r is the smallest. And which is the largest? Violet, because its speed is the slowest. If it is the slowest, so mu violet is the highest, largest. All other colors like red, then mu indigo, mu yellow, and so on, so lies in between. So now we come to, we'll be able to explain dispersion of light. So now let us get back to this figure, or say this figure. This is the angle of incidence for the white light. That means all the colors are together and they have made an angle of incidence I. Now for red light, now we know Snell's law. So this is, let us consider this is air. So we will call it, take it as 1. And say this is mu. Sorry, so this is 1. And this is sin. So from Snell's law, sin I to 1 into sin will be equal to, for red light, it will be mu r into mu r into sine. We call sine's angle of refraction as sine r. Now because mu r, and for violet light it will be 1 into sine I equal to mu violet into sine r. Now mu r is less than mu violet. So angle of refraction for red light will be more than angle of refraction for violet light. So you see, this is the angle of incidence, this is the angle of refraction. So the violet light will have less angle of refraction and red light will have more angle. So this is R violet, this is R red. So R red is more than R violet. So that means they will split, different color will split, because after the refraction, They will have to go in different angles with the make different angle with the normal. So the colors would split spatial in the space. So this phenomena is called refraction of light. Sorry, this phenomena is called dispersion of light. Now, if in case of a prism, this shows the illustration of prismatic dispersion. Refraction on the first surface will spatially split the white light into its constituent color. This is the reason. Refraction on the second surface will enhance their spatial separation further because they are now traveling from denser to rarer media. They will again be away from the normal as they're traveling from denser to rarer. So, this refraction at the second surface will further enhance their spatial separation. Now, it is of interest to note here that almost Newton first spoke of prismatic dispersion almost 3 centuries ago, 1700, from early 1700. Now, it is of interest to note here that almost 3 centuries later, the concept of prismatic dispersion, originally perceived by Newton, has now been central to impart tunability in the operation of lasers. And you have seen in one of the classes, earlier classes, that the wavelength, if you put a prism in the inside the cavity of the laser, then the prism actually splits different modes spatially, allowing the laser to go on single mode, and by changing the orientation of the prism or the output mirror, you could actually tune the color of the laser, that is the oscillating mode. You can actually change it, you can tune the laser. So it is the same concept which was introduced, which was perceived by Newton 3 centuries ago, is now finding application while tuning a laser. I think I will stop here today.